Okay, so I'm going to do the practice prac for you guys today. So what we're going to do first is part one. So if you have a look at your booklet, I've got mine over here. I've got someone's over here. If you're missing your booklet, come and see me. So we want to turn to page 150. The first thing we have to do is determine lambda max. Now lambda is our wavelength of light we're going to use. Every single compound that we put through the spectrophotometer is going to use a different lambda max. Now we need to use the same lambda value throughout all of our measurements to make sure that we're being accurate, okay? Because compounds absorb different wavelengths of light, different amounts, okay? So we want the maximum one to be the most accurate, and we want to keep it through the whole way, okay? Now, the first thing we're going to do is we're going to prepare 5 mils of an iron solution containing 2.5 mils of 0.2 molar iron chloride and 2.5 mils of water. Okay, so we're going to do that first. So I'm just going to get this stuff. So we need a test tube, 2 test tubes, and a test tube holder, which is just here. So here's our 2 things for part 1. So the first one, we're going to have 2.5 mils in that. So that we're going to need a graduated pipette. Alright, so this is our graduated pipette. Okay, we need a pipette bowl. One of those. Now, when we're putting it together, again, don't put it like that. The glass will break, it'll go through your hand. So hold it like that, push it in, like so. Press valve A, squeeze out all the air. Now, we don't take it straight out of the bottle. Don't. We're going to get some beakers and we're going to pour a little bit into a beaker and use that. So, a bit of iron chloride. Now remember, you're only using 2.5 mils, so you really don't need to take much, okay? Don't take 100 mils if all you're using is 2.5. And we need some water. So the first thing we're going to do is we're going to take the water, put the tip of the pipette into the water, press the valve S, and slowly suck it up. Now, we only need 2.5, so you're going to have to read from the bottom. Make sure you take 2.5 mils. Okay. Once that's done, press the E valve and let it all dribble out. Okay. Touch it to the side. Any capillary action will take the rest out. If it doesn't, that's fine. It's not meant to be. Okay. We just blow the rest out into the sink. Now we need to take some iron chloride. Now there will be a bit of water in your pipette, so we've got to wash it out. So the best thing to do is to take a little bit of the iron chloride and ditch it. Okay, that's going to take any of that water that's affecting our concentration and get rid of it. So now we're going to do the same thing. We're going to take 2.5 mils of our iron chloride. I'll just tilt this up so you can see what I'm doing. Okay, I hold it up here to eye level, press the E valve, release it to that point that is where we have 2.5 mils. Okay, once that's done, lower it down, press E, and it'll just dribble out. Press it to the side, like so. And if that's it, we leave that. Okay. So that is our blank solution. Okay. Now, what do we need the blanks for? We can see here that this is colored yellow. Okay. The compound that we're actually going to be looking at isn't colored yellow. It's a nice violet color. So when we measure it, we want the spectrometer to ignore that. Okay, so it's going to measure that as a baseline. And it's going to measure any of the change. And the change will hopefully just be that nice violet colored compound. Okay. Now, to make up the compound, we want, now the book says 10 mils of a solution containing 3 mils and 3 mils. I'm sure the smart ones among you know that 3 plus 3 does not equal 10. Okay. So what we're going to do is we're just going to change that to 2.5 and 2.5. So very similar to what we've just done. We're going to take up 2.5 mils of our solution. Again, I'll show you how. So I go up past the 7.5 point. Make sure there's no bubbles. And slowly drain it out, pressing the E valve until it's at the right level. I'm putting it into the right test tube. Do that, okay? Now, because we made up our water one, we now need to make up one with salicylic acid. Okay, so for you guys, preferably get a fresh beaker. I'm just going to wash it out with a bit of salicylic acid. Now, what you guys want to do is, again, wash this out with the solution that you're going to be using. So I'm just going to squirt out any of the iron that's in there. I'm going to bring some up. Now, you'll notice how it's a nice violet color, okay? That's because there was iron in there. Now, we don't want that, so we're going to get rid of that. Hopefully you didn't contaminate your salicylic acid like I did. So it might be worthwhile actually washing it with a bit of water first, okay? But again, same deal, suck it up a little bit past the 7.5, let some out, and put it into our iron solution. Now the iron's going to react with the salicylic acid. It's going to form iron salicylate. Iron salicylate is that nice purple color. Okay, I've got a bit here. You might be able to see the tint on that. But in with the iron, it looks like that. So it's that nice kind of purpley yellow. Okay, it's a bit of a browny sort of color with all that yellow. But when it's by itself, it's purple. Okay, so we're now going to do the spectrophotometer bit. Okay, so what we do, we need 1 cuvette for calibration. We need 1 cuvette for the sample. So I've got 2. Now during your assessment, I'll have the calibration one ready to go so that you don't have to spend time calibrating it all the time. So what we do, put a little bit in. If it's dry, you can just put it straight in. If there's a bit of water, I'll show you what to do on the next sample. Okay, so that's our calibration. Now let's say we've got some water in here. What we do, we just put a little bit in. Okay, just maybe a bit more than that. Just a little bit like that. Swish it around, down the sink. Okay, that ensures that any water in there has been removed with the solution, so anything that's left should mostly be our prepped concentration solution. Fill her up. Preferably to about 90%, okay? And then we put it in the spectro. So we put in the spectrometer, so we warm it up, which I'll do beforehand. We put it in, we zero it, so that's calibrating it. Take it out, put in our sample. Now we're looking for lambda max. Okay, so I'll show you a video of that shortly. I'll splice it in. Basically, we're looking for the maximum absorbance. Okay, you want to find that wavelength that absorbs the most. Okay, so from this class, from previous ones, it was about 520 to 525 nanometers. We're going to probably use 522.7, which is what I was using earlier today. Okay, so that is part one. Okay.
So here's the results for part one. So after we blanked it, we put in our first sample, we found our lambda max to be 522.7. Okay, so that, as long as it's around that point, okay, experimentally it can differ a little bit between groups, you know, anywhere from 520 to 525 is acceptable. And then you can just write the absorbance. You don't necessarily need that for this one, but the main thing we have is lambda max, because we need that lambda max to tell us what wavelength to measure the rest of them at. Okay, we need to keep it the same throughout all of our measurements. Okay, the main thing for having this absorbance value is just to check that it's in the right range. Now, absorbance is in itself a logarithmic scale. Okay, basically an absorbance of 1 means that 90% of light is being absorbed. Absorbance of 2 is 99%. Absorbance of 3 is 99.9%. Generally, we like the absorbance to be about 1, no more than 2, and generally, for our highest concentration, no less than about 0.5. Okay. Now, the reason we don't want it above 2 is because we start to have to try and tell the difference between 99.9 and 99.8 and 99.7. Like, this is a change in the third or fourth significant figure, which reduces the accuracy. Okay. And so that's why we just need to check. If that was about 2 or more, I'd dilute everything down a little bit, okay? But I've already gone through, I've already figured out all of the absorbances for you for this one. It's a 1.645, that's in our range, that's our highest concentration we'll use, so that's okay.
Okay, so for part two, we're going to need 3 beakers. We need our 0.2 mole iron solution, our 0.002 mole salicylic acid solution, and some water. We're also going to need 5 beakers labeled A through to E. Okay, so what we're going to be doing is making this calibration curve. Now, what we're doing, we're going to add the salicylic acid in different concentrations to our iron solution. We're going to make them up to the same volume each with water. And then we're going to measure the absorbances and plot them. Okay. So what we do, have a look at our table, which is on page 116. Okay. It tells us exactly what we need. So for part 2, creating a calibration curve, we need our 5 test tubes labeled A through E, using a graduated pipette, place the appropriate amounts into each test tube. So each of them requires 4 mils of 0.200 molar iron chloride. Okay, so I'm going to just take a little bit up, wash it out with the pipette, drain it out. And now we need 4 mils, so we need to go from 10 up to 6. So I'll go a little bit fast, so a little bit past where it is, drain it out till it's at the right point, and place it in the test tube. so right now I'll empty that back in. Pour a bit more iron chloride. And I'll keep going. Okay, so in each of those test tubes, we now have 4 mils of iron chloride. What we're going to do, clean this out a little bit because we don't want our iron contaminating our salicylic acid. So just suck up a little bit of water to wash it out. So otherwise we'll get that purple in the pipette like we did on the last one. Okay. Now we'll suck up a little bit of the salicylic acid, drain out. And because we don't want to contaminate it too much, we're just going to wash it out once more with some more salicylic acid. Okay. Now I can actually suck some up. The first one we need 3.6 mils. Okay, so we want to go up to 6.4 on the pipette. And we're going to put that into the first one. Okay, so we get a nice purple solution formed. Continue on, the next one's 2.8. So I need to go up to 7.2. Okay. That was good, that was right on for me. Next we need 2, so we need to go to 8 line. Yep. Next is 1.2, so we have to go up to 8.8. Yeah, putting that in that one. Now the last one requires 0.4 mils, but if you look at this pipette, I'll try and rotate it around so you can see it. See how it only goes to 9.5, so we need it to go to 9.6. So what we're going to do, there's 2 ways you can do it. You can either get a finer pipette, which I'll provide you during the assessment, or you can just suck some up to wherever and very carefully let out 0.4 mils. So that's me, that's what I'm going to do. So I need to, like that, okay. And I'll let that drain out. Now, so that's the salicylic acid. So once I mix them, turn it around so I can show you this. You see that there's a nice looking sort of gradient, but the volumes are all different. Okay, so we're going to add water to make up the difference so that they're all the same volume. So firstly, we need to wash it out. So suck up a bit of water, drain it out. Do it again, bit of water. Make sure you got all your beakers and test tubes labeled, okay? I know you guys don't like to, but that's kind of too bad. It's much easier if you label it. take the 3 seconds it takes to label it, and you won't mess anything up. Okay, so again, first one we need to take up 0.4 mils of water. So I'm just going to do the thing where I drop in 0.4 mils. There we go. Give it a mix. The next one requires 1.2. Okay, give that a mix. We then need 2 mils of water. We then need 2.8. And lastly, 3.6. So we've got our 5 solutions, A, B, C, D, E. So you can start to see, actually I don't know if you can see it properly there. You can see how it's a very nice gradient from dark to light. Okay? So this one's our most concentrated to our least concentrated. They should hopefully give us different absorbance values in a linear fashion. Okay, so I'll run these values. Basically, we're going to put each of them into a cuvette. So again, each group you're going to have just one. Then get your thing, put in our little put in our sample. If it's dry, if it's not dry, we put a little bit in, swish it around, pour it out, then put in our actual sample. Okay, so I'll run these, I'll get some values for you all, and then we'll analyze it.
Okay, so the results for part 2, we've got our absorbances A through E. So we see that they're decreasing quite linearly, which is great. We also need to plot them against some concentrations. So mainly this concentration here, the concentration of the iron salicylate. How do we get that? How do we get these concentrations? Well, we use this formula here, C1V1 equals C2V2. That's our dilution equation. Okay, we're going to rearrange it into C2 equals C1V1 over V2. Now, what's our C1V1? What are we dealing with? Well, if you think about the reaction, 0.2 moles per litre of iron chloride is mixed with 0.002 moles salicylic acid. Okay, that iron chloride is in 100 times excess. There's so much of it. So we're going to use a very small amount of that when it actually comes to the reaction. So what we're going to do is we're going to find the volume of the salicylic acid using C2 equals C1V1 over V2 and use that in our graph. Now, how do we do that? Okay, so we take the concentration of our salicylic acid, multiply it by the volume of our salicylic acid that we used. So for test tube A, that was 3.6. We're going to divide it by the final volume. And in this case, the final volume is 4 plus 3.6 plus 0.4, which is 8. So we do that, we get 9 by 10 to the negative 4 moles per litre. Okay? Now, that's our concentration of salicylic acid, so our C7H6O3. The salicylic acid is this part in the equilibrium. Okay? The iron and the salicylic acid will react in 1 to 1 to form iron salicylate and a H+. Okay. Now, because we put so much iron in, it's going to push this whole reaction towards the product. Okay? So effectively, with the little bit of salicylic acid that we put in, all of it is going to be converted to iron salicylate. Okay? Now, in reality, it's not all going to be converted, but about 99.99999% will be. Okay? So we're just not going to worry about that last little bit. So we're going to effectively say that the concentration of salicylic acid is the concentration of iron salicylate. So I've gotten that concentration there for you for the first one. So 9 by 10 to the negative 4. Now let's do the next one. So we want to find out the concentration of B. Okay? So we're going to do C1, so 0.002 times V1, 2.8, divided by the total volume, which is 8. So 0.007, or 7 by 10 to the negative 4. Okay? Now, because the concentration of salicylic acid is equal to the concentration of iron salicylate, that number is going to be the same. Okay? Now, if we do the rest, we find out that it follows this pattern for this particular one. Okay? So it follows that pattern. Now, it tells us here, we then plot iron salicylate concentration as our independent versus absorbance, which is our dependent. Okay? So, I'm going to do this one horizontally. You can do it vertically. It does not matter one little bit. Now, when we're doing a graph, we want to have independent down here, dependent up here on our y-axis. Okay? So in this case, we're going to put concentration along the bottom. So we're going to label as concentration of Fe C7 H5O3 2+. Now put our units in moles per litre, or you can just put big M. Okay, either one's acceptable. But remember, you always need to label your graphs. Now, up on the y-axis, that is our absorbance. Absorbance has no units, it's unitless. Okay? Now we want to figure out what divisions we're going to use. So let's have a look. So we need to go up to, on the concentration, 9 by 10 to the negative 4. Let's see how many squares we've got. So 40. We've got 40 squares. So it might be easy for every 4 squares, we set the concentration as 1. So that'll be 1 by 10 to the negative 4, 2 by 10 to the negative 4, so on, and so forth. Okay? 10 to the negative 4. Okay, so you see the main thing is that we want to set the graph to be as readable as possible. Okay, we want to take up all the space that we're given. But the more space we use, the more accurate it becomes. Okay? Now absorbance, we need to go up to 1.589, so let's have a look. So it goes up to 40. I reckon after 20, that would be an absorbance of 1 would probably be best. So there, an absorbance of 1, so that would mean that would be 0.5. that would be 1.5, so on and so forth. So we could say 0.1, 0.2, 0.3, 0.4, 7.8, 0.9, 1. Okay, so just setting up our graph like that. So we can see that we're going to be using most of the space here. So now let's put our values on. So 9 by 10 to the negative 4 is 1.589. So about there. Okay. For the next ones, alright, so you can see we've got a pretty good straight line. So let me put it like that. Okay, so we want to put in a line of best fit. Okay, so if we have a look, our last one's a bit low. Okay, might be a bit of an outlier. But for our line of best fit, we want to go through 0 because at 0 concentration there should be 0 stuff there. So let's do this. Now when we're drawing a line of best fit, the thing we want is the perpendicular distances above and below to be the same, okay? Or the sum of them. This one, I reckon this would probably make a good line of best fit. Now remember, I'm just looking for your process. You don't have to get it super, I'm not going to mark you on everything being 100%. But we can see that these two are close to the line, these two are slightly above it, this one is below it, okay? So that seems to be about the best line of best fit, okay? So, that's our line of best fit, that's our calibration curve. Now, in our next section, if we go, let's say we've got something that resolves to 0.9, we can then read the graph, okay? So I'll show you how to do the pack first, and then we'll...
Okay, so this is part 3. So this is where we're actually going to get some values, and we're going to calculate K cubed. Now, we need 5 test tubes labeled F through to J, so F, G, H, I, J. We need our 3 beakers with our stuff in it. This time we're using 0.002 molar iron chloride, okay? The reason we use, like I've said it a few times, but the reason we use the concentrated stuff in parts 1 and 2 is to push the equilibrium all towards the products. So remember Le Chatelier's principle, if we add reactants, it'll push towards the products. Now, in parts 1 and 2, we'll be using 0.2 molar iron and 0.002 molar salicylic acid. So there was at least 100 times the amount of iron than there was salicylic acid. So there's all these reactants pushing the equilibrium towards the products, okay? We do that so that most of the salicylic acid gets converted to iron salicylate, which is our purple compound. This one's going to be a bit different, okay? Because what we're going to do is use the lighter stuff so that the equilibrium is more, well, equal. It's more of an equilibrium system. It's not this one-sided thing, and most of it's just on one side, okay? Now, the first thing that I have to do, and I'll do this on the day, so you guys don't have to, is create a little calibration solution, okay? So what we'll do, I need another test tube. Luckily, I have one just here. So I'm just going to create a little calibration thing for this. It's just 2.5 mils of the weaker iron chloride. Now, why do we have to do a different one? Well, remember, the calibration is taking away the stuff that we're not using, okay? And so in this case, we're not using lighter iron. If we use the concentrated stuff, it's going to give us negative absorbance values, okay? So, we'll just quickly clean this out, take a bit of water, clean it out. And we're going to add 2.5 mils of water. And we've got a nice lighter colored calibration solution. If we compare it to the other calibration solution, you can see that there is a bit of a difference. Okay, this one's much more concentrated. So I'll leave that there. Now, in F through to J, we want to put in the values that are at the bottom of page 116. So we're going to put in 5 mils of the 0.02 molar, 0.002 molar iron 3+. So 5 mils into each test tube, and then we're going to put in those other values. Okay. So I'll get to work on that. So again, before we start, just clean out our pipette and take up a little bit of the iron solution, drain it out. It's one of the few times where we actually have to push air through to push stuff out. That's when we're cleaning it. Okay, suck it up. We want 5 mils. If you get a bubble in the solution like I just did, just let it all out. And then push some air through it, okay? Just to get rid of that bubble. Sorry about that little interruption. So what we're going to do is put in that 5 mils per 5 mils of iron chloride per test tube. Okay, so that's the iron chloride, that's done with. Now we're going to put in our salicylic acid. So from F through to J, it goes from 1 mil to 5 mils. Okay, so I'll move that out of the way so I don't accidentally put salicylic acid into our calibrating one. I'll suck a bit of water up into this to clean it. Okay, so we will suck a bit of salicylic acid up, let it run out, and just blow a little bit out at the end. Okay. I should point out that when we're using pipettes like this, it's designed to have a little bit of liquid left in the tip. Okay, so don't get this overwhelming urge to blow all of the liquid out, because that will introduce inaccuracies. Okay. So the first one had 1 mil, the second one's got 2 mils. You can tap it against the side if there's a little droplet there. Okay, like what I'm doing here, just tap it against the side. Listen to a little jingle. And lastly, we want 5 mils. Okay, so because we've been putting in different amounts of salicylic acid, we will still see a little bit of that gradient. I don't know if you can see it well in this light, but we can definitely see that because we went from 1 mil in this one, the iron salicylate is a lot lighter. Okay. Now, we also need to put in some water, okay, to wash out our pipette a little bit so we don't introduce more salicylic acid. So this time we're going to go from 4 mils down to 0 mils. First one needs 4 mils of water. So we should get 5 test tubes with 10 mils in each. So 3 mils. 2 mils. And lastly, 1 mil. Okay, so now we've got our 5 solutions. Just like that. Okay, give it a bit of stir, bit of a swirl. And we start to see that gradient a little bit better. Okay, so you can see the lightest on this end and the darkest on this end. Now, hopefully, when we put that through the spectrometer, we get some values that we can actually then calculate KEQ from. Okay, so I'll run those through the spectrometer, I'll get the data, and then go through how to analyze it.
Okay, so here's the absorbances for part 3. Okay, so we've got all these absorbances here. Firstly, before anything happens, we need to write our K equation. So remember, products over reactants equals K. So in this case, it's going to be the iron salicylate. So concentration of our FeC7 H5O3 2 plus multiplied by H plus. Okay, these are going to be the same concentration over the concentration of Fe3 plus times the concentration of salicylic acid. Okay, so these are all the values that we need to get to calculate KEQ. The very first one, the concentration of iron salicylate, we get this from this table. Okay, we basically take our absorbance, read the concentration off the table. So 0.405, let's have a look. 0.405, okay, I'll try and put it where you can see it. So the absorbance is 0.405. It looks like it connects just past 2, okay? So let's say it's 2.05 by 10 to the negative 4. Moles per liter. Now it's 0.596. So very close to 0.6. It comes across over here. so that looks to be about 3.1. Let's put that down to 3.1. Uh, 0.758, so 758 comes across to about there. Which gives us a value of about, what would that be? About 3.9 by 10 to the negative 4. Okay. Now, I'll let you do the other ones by yourself. So we'll work on these three to begin with. Now, we need to calculate the concentration of iron 3+. Okay. Iron 3+, you will start off with some, and then some will be used up to form the iron salicylate. Okay. So, the way we do it, to find Fe3+ at equilibrium, we find the initial amount of Fe3+ and take away the concentration of our iron salicylate. So what is it? What is our amount of iron to begin with? Let's have a look. So 0.002, but it's diluted. So again, we need to do this dilution thing, so C1 V1 over V2. In this case, we'll just end up with 0.001. Okay, so that's how much iron we start with. So Fe at equilibrium will be 0.001, take away 2.05 times 10 to the minus 4. Okay. Let's put that into our calculator. So like that. We get that. So that's 7.95 times 10 to the negative 4. Okay. For test tube D, we're going to use the same initial amount and then take away the value that we got. So instead of being 2.05, it will be 3.1 times 10 to the negative 4. So 6.9 times 10 to the negative 4. Okay, we're hoping these numbers go down because we had more for iron salicylate, and so there should be less iron left. And 6.1 by 10 to the negative 4. Okay, that's the iron. Nice and easy. So the concentration of salicylic acid, okay, it's a 1-to-1 ratio. So the concentration of salicylic acid at equilibrium equals the initial amount, take away our concentration of iron salicylate. Now, if we have a look at the initial amount of salicylic acid, okay, in this case, it's going to start off with 0.002, and we're going to do a 1 in 10 dilution. Okay, so it should be 0.0002, which is 2 by 10 to the negative 4. So C7H6O3 at equilibrium should be our initial amount. So this is just for the first one, mind you. So 0.002, take away 2.05 by 10 to the negative 4. Okay. I'm sure you can see the problem here. This is going to end up with a negative number. Oh, no, not quite. No, so this is one of the problems with putting zeros in. 0. Yep, so that ends up with a negative 5 by 10 to the negative 6. Okay? Basically what this means is that I wasn't accurate enough with that number. Okay? You'll find that in the practice one, this will happen quite frequently because the KET is actually very high, so it's not a very accurate one. But it shouldn't happen in your assessment. Okay, let's try the other one. So for G, because we used 2 mils of salicylic acid and our total was 10 mils, it'll be 0.002 times 2 divided by 10. So it should be 0.0004. Take away 3.1 by 10 to the negative 4. Which should actually give us a number this time. Okay, so we have 0.00009. Okay, so there's not much salicylic acid left. For H, we're going to do the same thing. So we had 3 mils of salicylic acid going up to 10. So it should be 0.0006 minus 3.9 times 10 to the negative 4. Should be 0.00021. Okay, 0.00021. So we're going to have to strike F from the record. Okay, we're not going to worry about that because we've got a bad number. If that happens in your assessment, do the exact same thing. Just strike it and write down why. Okay, tell me why you've struck it from the record. Anyway, for KEQ, we now have to put in all of our numbers. Okay, so we have our concentration of iron salicylate from here. So I'll just put a line through F. We have our concentration of H+, because it's the same as the iron salicylate. Okay, because this reaction happens 1 to 1. We don't start with any, and so we're going to end up with the same amount. Now, you won't have to worry about the H+ thing in your assessment, that won't be there. Fe3+, we take it from this table, down here, and salicylic acid, we take it from this table over here, okay? And so, for our KEQ, let's put it together. So, products over reactants, so remember to pork it. So, iron salicylate, 3.1 times 10 to the negative 4, times 3.1 times 10 to the negative 4, over 6.9 times 10 to the negative 4, times, what would that be? Actually, I'm just going to put it in as that. If you're using the zeros after the decimal point, just make sure you count them correctly. A lot of people last year didn't. And so for that KEQ value, we actually get that as a number. Okay? So it's 1.5475. Okay? Now, let's do it for the next one, see if there's any coherence. Now, I don't expect there to be much coherence. I'm mainly looking at your process, not your actual answer. But let's do it again. So 3.9 times 10 to the negative 4 times 3.9 times 10 to the negative 4. Over our iron, which is 6.1, times 10 to the negative 4, times our salicylic acid of 0.00021. Okay? And we get 1.1873. Okay? So you see that there, you might look at that and go, okay, they're not in accordance at all, but in chemistry, where things can range from 10 to the 50 down to 10 to the negative 50, the fact that they are on the same order of magnitude and they're only off by a little bit, that's actually pretty good. Okay? So if you get results that are like that, you know, within the same order of magnitude, that is a good thing. Okay? At that point, you want to do your KEQ average. So you just average these. If I need to tell you how to do average, I'm going to send you back to year Okay? And that's pretty much it. There will be some questions. All the questions are answered in either this booklet or in what I've been speaking about. Okay, I've told you most of the answers to the questions. So study this video, study this book, write notes in this book, you can bring this book in. Okay? And whoever actually left this book without their name, I'm going to show you your writing. So if you're missing this book, you've got all my answers in there, so you're going to be a lucky one. Come and get it off me, okay? Well, thanks for that. Good luck in your assessment. Remember, it starts Monday,